Okay, so we're back with another video. Today we're going to be talking about elastic collisions once again, but we're going to deal with the relative motions of the objects, before and after the collision. So we're going to pick one particular frame of reference, and that's going to be the center of mass. We are going to be looking at the whole situation from the perspective of the center of mass. All right, we're going to be looking at what the relative motions are, the relative velocities are of the masses, both before and after the collision, because there are some fundamental rules that are true, that always must be true before and after the collision. For example, first I'm going to show you on this side what the rules are. So this is a person asking a question, but he says in a two-body collision in a center of mass reference frame, the momenta of the particles are equal and opposite to one another both before and after the collision. Okay, so the momentums from within the perspective of mass, the momentum of mass 1 and mass 2, okay, that must have the same magnitude after the collision as well. The only thing that will change is its sign, its value sign, because the directions will be opposite after the collision. So he continues to ask, is the line of relative motion necessarily the same after collision as before? Under what conditions would the magnitudes of the velocities of the bodies increase, decrease, or remain the same as a result of the collision? And so somebody answers this question and he says, yes, the line of relative motions necessarily are the same after collision as before. In accordance to the law of conservation of momentum, the total momentum of the particle having mass 1 and particle having mass 2 before the collisions equals their total momentum after the collision. And then the changes in momentum of the two objects have equal magnitudes and opposite signs because they go in opposite direction. And he says a necessary consequence of the law of conservation of momentum. It's a necessary consequence of the law of nature, of the law of the conservation of momentum. And therefore, the line of relative motions necessarily are the same after collision as before. So from within the perspective of center of mass, the velocity, so the relative motion of mass 1, so mass 1 seems to be approaching you at a certain velocity, mass 2 will seem to be approaching you at a certain velocity, all right? And after the collision, those velocities, those relative velocities must be the same. The only difference is the sign will be different, will switch, will flip because the directions will be opposite. So now we're going to theoretically verify this, whether or not this is true. And I'm going to be comparing two models. We have the conventional science model and the draft science model. All right, so where is mine? There it is. First, we're going to start simple with equal masses, situation in elastic collision with equal masses. So let's say that mass 1 is 1 kilogram, mass 2 is 2 kilograms, all right? And their initial position is, well, they are 5 meters apart. So the distance between the initial distance between mass 1 and mass 2 is 5 meters. So where is the center of mass? Well, obviously it's right in the middle. So it's going to be at the center of mass is located at 2.5 meters. Now let's say that mass 1 is approaching mass 2. All right, so mass 2 is stationary. Mass 1 is approaching mass 2 with a velocity of 1 meter per second. Okay, that would mean that, okay, after 1 second, so over here, you can see this little red dot represents mass 1. This line represents mass 2, which is stationary at the 0 line. All right, so 5 meters is the initial distance. This green dot here is the center of mass, located at 2.5. Sorry, that's in the negative direction. You have to 1, 2, and 2.5. That's the initial center of mass position. Now, after 1 second, mass 1 will have traveled 1 meter or 1 centimeter. All right, so now the distance between mass 1 and mass 2 is 4 meters. All right, so the center of mass is now located at 2 centimeters or meter. Then 1 second later, mass 2 will have traveled another meter. So now it's located at 3. So the distance between mass 1 and mass 2 is now 3. So the center of mass is located at 1.5. Okay, so now, so you can see that the center of mass itself is traveling with a speed of 0.5 meters per second. Now, so the initial distance between the center of mass and mass 1 is 2.5. Okay, 1 second later, center of mass is over here, and the one mass is over here. So now the distance between them is 2 meters. Okay, so right, we are going to observe everything from within the center of mass. So we are at the center of mass. The initial position of mass 1 was 2.5 meters. 1 second later, mass 1 is now 0.5 meters closer to you. Okay, so that means that the relative velocity of mass 1, okay, it seems to be as if mass 1 is approaching you with a velocity of 0.5 meters per second. Now, mass 2, which is actually stationary, right? But from within the perspective of mass, from within the perspective of center of mass, gotta stay focused, all right? So the initial distance was also 2.5. 1 second later, you are now 0.5 meters closer to mass 2, all right? So you are approaching mass 2 with a velocity of 0.5 meters per second, okay? So the relative velocity of from within the perspective of the center of mass, right, is that mass 1 is approaching you with a velocity of 0.5 meters per second. Mass 2 is approaching you with a velocity of 0.5 meters per second, right? So that's the same. And that will, all right, so, and then the momenta will be 5 and 5. And then after the collision, the same thing will happen, all right? Mass 1 will seems to be going, mass 2 will seems to be traveling away from you at a distance, at a velocity of 0.5 meters per second, and mass 1, which is actually stationary now because it has given all of its energy to mass 2, all right? But from within the center of mass, it seems to be that mass 1, which is actually stationary, is leaving you with a velocity of 0.5 meters per second. So the velocities both before and after collision will be exactly the same. I hope you can follow along. It's easy to get confused. So now let's take a look at unequal masses. All right, that's always the case where a disagreement happens. So we have conventional science and draft science. Now, the situation before the collision is in both models should be exactly the same, right? That is to say, so now let's take the example of mass 1, mass 2. Mass 1 is 1 kilogram, mass 2 is 2 kilograms. Mass 1 is approaching mass 2 with a velocity of, well, let's say also 1 meters per second. I wrote 10 meters per second, but let's say 1 meters per second so that we can follow along on the ruler. Okay. So now, where is the center of mass? We have 1 kilogram, 2 kilograms. All right, where we can calculate the center of mass with this formula: mass 1 times its location plus mass 2 times its location divided by the total masses. So mass 1, its location is at 3, but you can take 0 because the distance between them is 3 meters. If we take 0 for mass 1 as location and 3 as the location for mass 2, that's the same. If we apply this, then we find out that the center of mass is located at two-thirds of the distance. All right, so the initial position of mass 1 is located at 2. Right, this is something that draft science should also agree with. Center of mass, right? If this is 1 kilogram, 2 kilograms, and their distance is 3 meters, then the center of mass is located at 2/3 of the total distance. right? So that means that the center of mass will always be located at 2/3 of their distances. Okay, so now you can check this for yourself, right? You can check the initial position is of mass 1 is over here, and mass 2 is over here. It's stationary, all right? So after 1 second, it traveled 1 meter, and then the distance is only 2 meters apart. So now 2/3 of 2 meters is going to be over here somewhere, and then 1 second later, it's only 1 meter apart, and then again 2/3 of this distance. That will be the place of the center of mass, but you will find out that from the perspective of the center of mass, velocity 1, right, mass 1 is approaching you with a velocity of 6.66 meters per second. And mass 2 is approaching you with a velocity of 3.33 meters per second, which is the mass which is actually stationary. But from the perspective of mass, of the center of mass, it is approaching you with a certain velocity. All right, that means that their momenta, right? Mass 1 is 1 kilogram, so it's 6.66 kilograms meters per second. Mass 2 is approaching you at 3.33 meters per second. Its mass is 2 kilograms, so times 2 is also equals 6.66 kilograms meters per second. All right. Now, in draft science model, it should be the same. Okay, this is the initial state. We have 1 kilogram, 2 kilograms. The initial distance between them is 3 meters. The center of mass is located at 2/3 of this distance. Okay, so the relative velocities from within the center of mass 1 is approaching you with a velocity of 6.66 meters per second, and mass 2 is approaching you with a velocity of 3.33 meters per second. That should also be true. Draft science should agree with this. Okay, that these are the relative velocities from within the perspective of the center of mass. Yes, so for the momentum, draft science would add these together, and so we already have around 13 momentums, but the initial momentum was only 10. So yeah, but we're not going to deal much with momentum for now. We're going to deal with the relative velocities, because those should be the same after collision as well. So that was the rule, right? Which is necessary, which is important also for the conservation of momentum, that the relative velocities before the collision should be exactly the same. It should have the same magnitude after the collision. So back to the conventional science model. After collision, so conventional science predicts that for a 1 kilogram that collides into a 2 kilogram, right? If the initial velocity is 10 meters per second, and this one remains stationary, right? Then after the collision, the mass 2 will lift off with 2/3 of the velocity, and mass 1 will reflect back with 1/3 of the velocity. Okay, so mass 1 reflects back with minus 3.33 meters per second. Mass 2 continues to travel in the same direction with 6.66 meters per second. You can check again the relative velocities. Where is the center of mass? Where is the center of mass located at 2/3 of the distance? All right. And so you will find out once again that from the perspective of the center of mass, after the collision, mass 1 is now seems to be going away from you with a velocity of 6.66 meters per second, and mass 2 is going away from you with a velocity of 3.33 meters per second, which is the same as before the collision. We had plus 6.66 and minus 3.33 meters per second. And after the collision, we have minus 6.66 and plus 3.33. The relative velocities are exactly the same before and after the collision, but the directions have changed. Now, within draft science model, he has exclusively stated, he has stated that in an ideal situation, so we have to look at this as this is an ideal elastic collision, all right? The predictions for conventional science right? That, you know, after the collision, mass 2 will continue to travel with 2/3 of velocity, and the mass 1 will reflect back with 1/3. That's what should happen in an ideal situation, right? So we are in space, there is no resistance, okay? There is no air resistance or anything. Perfectly equal masses, you know, everything is perfect, and that should happen. Now, draft science has stated that if you have a one mass, a 1 kilogram and 2 kilogram, and this one is stationary, all right, and this one travels at 10 meters per second, all right. So if all of its energy is transferred into mass 2, then after collision, mass 1 should stay stationary, and mass 2 should lift off with 5 meters per second, all right, such that the initial momentum would be 10 kilograms per second, all right, and after collision, mass 1 has 0 velocity, and mass 2 is going with a velocity of 5 meters per second. So, and mass 2 is 2 kilograms, so 5 times 2 is 10 kilograms, is 10. So that's going to be the momentum, 10. So for draft science, momentum is conserved, all right? The initial momentum is 10, and after collision, the momentum is 10. So again, draft science has stated that after collision, right, the one mass should be stationary. In an ideal situation where all of its energy is transferred, it will not reflect back. It will be stationary, and mass 2 will lift off with a velocity of 5 meters per second. That's what he has stated. Now, what is where is the center of mass? So now mass 1 is stationary, right? 1 second later, mass 2 has traveled 5 meters or 5 centimeters, right? Where is the center of mass? It's not 2/3 anymore. Let's see. It's right here. It's at 3.33, I believe. And then 1 second later, right? The distance is now 10 meters. Wait, it is 2/3. It is 2/3. Sorry, I'm being distracted. 1 meter, 1 second later, the distance is 10 meters, right? So what you will find out is that the relative velocities from the perspective of center of mass is minus 3.33 and plus 1.66. All right, so if we assume that, yes, mass 1 stays stationary after collision and mass 2 lifts off with 5 meters per second instead of 2/3 and the reflection of 1/3, then we find out that the relative velocities, right, then mass 1 seems to be leaving you with a velocity of 3.33 meters per second, and mass 2 is leaving you with a velocity of 1.66 meters per second. And as you can see, it's not the same, those are not the same relative velocities as before the collision. Before the collision, we had 0.66 and minus 3.33, and after collision, we have minus 3.33 and plus 1.66. They do not match. They are not the same. So I think there is a theoretical problem here. All right, so the same with the momentums. They do not have the same magnitude. It's actually going to be half. So after the collision, the velocities end up, yeah, they are half the velocity. They're half the initial velocity. The relative velocities after collision is half the velocities as before collision. But it should be the same, as it is important for the law of conservation of momentum. And that's what I wanted to point out, that there is a theoretical problem, right? The relative velocities do not match each other before and after collision. And I just wonder what the reaction will be. Well, I do not wonder, actually. He will obviously, yeah, I guess we will see, but I consider this as a theoretical problem. All right, that's all I wanted to point out. So it's a long enough video, and thanks for watching. Stop the recording.